Good morning, friends and participants of the Global Young Scientists Summit 2022. Welcome to the panel discussion on the next generation grid. My name is Yo Lin Weng, and I'll be the host today. This year, the summit attracted a record number of participants of 1,600 from 38 countries. And today we have about 300 participants joining this online panel today. So we all know that climate change has posed an existential threat to us. And the power sector is one of the biggest contribution of global greenhouse gas. So there's a need for us to transform our power grid into a modern grid so as to be able to take in a lot more renewable and green energy. And this morning, we have three eminent speakers to share with us their insight on the future, the next generation grid. So first we have Professor Baliga. He's a distinguished energy university professor from North Carolina State University. And Professor Baliga is also the recipient of IEEE Medal of Honor in 2014. Next, we have Professor Stanley Whittingham, a Sani Distinguished Professor of Chemistry and Material and Engineering at Binghamton University. Professor Whittingham is also the 2019 Chemistry Nobel laureate. Last but not least, Professor Rong Hui, MediaTek Endowed Professor and Chair of Power Electronics at the Nanyang Technological University. He is also the recipient of the 2015 IEEE Technical Field Award in Power Electronics and the 2010 IET Compton Model. So to the panelists, thank you for agreeing to be on our panel discussion today. So I will call upon each of them to give a 5-minute sharing on their area and also on the insight of the next generation grid. So may I invite Professor Baliga to share his insight first. Professor Baliga, over to you.
So good morning to all the participants. Could the organizers put up the slides I sent you? Is that possible? Very good. So stay on the first slide, please. So what I'd like to do in my 5 minutes is to tell you that at North Carolina State University, we've actually been working on the power grid for about 15 years. And one of our major programs here was sponsored by the National Science Foundation. It was a $50 million program that ran for 10 years, and it involved 5 universities across the country. And our goal was to create what we call the future renewable electrical energy distribution and management system, or a freedom system. And our concept was to create what we call a plug-and-play microgrid architecture. So to give you an analogy, where we often use our flash drives, the sticks that you put into the computer, and they work seamlessly, they get powered, they exchange information, and so on. So that is done, of course, with signal level processing. What we wanted to do is create a similar architecture for very high power levels. And the reason is that today a consumer cannot plug in a solar panel into the power grid or even an energy storage device. The utilities will not allow that because it creates instabilities and difficulties for them. So the key component that we came up with to allow us to do this is known as the solid state transformer. That's written on the upper left corner of this chart. And I'll talk more about this. But that is a very smart semiconductor-based transformer, unlike the present transformers made of copper and iron. So with this transformer, we can control the voltages and currents very precisely. and it is something that enables preventing any instabilities. So I'll tell you a little bit about this solid state transformer concept and what we have done to make it successful. But we realized that to create a successful microgrid, we also needed to be reliable and safe from faults in the system. For example, a storm might come and a tree limb might fall across the power line somewhere in the microgrid and create a problem. So we want to isolate such faults, and to do that, we created what's called a fault isolation device. So these devices we felt had to be made with new semiconductor material, not silicon. Silicon is very good for many things, but not for this kind of voltage and power level. So we worked on silicon carbide and gallium nitride power devices. So the next slide gives you a little more about this. It shows here in the diagram the solid state transformer.
Okay, so perhaps we should invite Professor Whittingham to share his insight first. Professor Whittingham, over to you.
Okay, thank you. I'm not using any slides, so let's see how it goes. So I want to really talk about lithium-ion batteries, what they can do to help the grid, but it's perhaps good to remember the lithium-ion batteries really enable the communications revolution. So they provide the storage for that, so everyone has one or two of the lithium-ion batteries with them. And really, if we're going to solve climate change, clearly we have to adapt ourselves, but we also need to reduce the amount of temperature increase. We'll have to use cleaner fuels, which means we're going to be using probably renewables such as wind and solar. Those are both intermittent. So we will need storage. The largest storage by far is pumped hydro, but that's not portable and is not available in many places. So we need, in particular, batteries. And right now, lithium-ion batteries are dominating the energy storage arena. If you think about the largest one, which is, I think, is now 1.6 gigawatt hours, it's in California, just south of San Francisco. It's operating well, and I understand is financially viable. So grid storage that works there. The other areas clearly where batteries are going are into electric vehicles, and there's now renewed in what we can call a 1,000,000-mile battery. This would enable your vehicle, whether it's a truck or a car, to be permanently connected to the grid, except when you're actually driving. So it would act as a buffer on the grid and maybe help your home at the same time.
Okay.
But the challenge we have, it takes 50 to 80 kilowatt hours of energy to make a 1 kilowatt hour battery. So we have to change that. Part of that problem there is the materials may go 20 to 50,000 miles from the mine to the finished product, which is not sustainable. So the challenge we really face is to build what we'll call more localized supply chains. So these are maybe in, say, the Americas or in Europe. Asia obviously is doing very well there. So, you know, we have to work hard on that and enable trained people to spread around the world to do it, because outside of Asia, there's not enough workforce knowledge either in battery manufacturing or in the supply chain itself. So we have to work on that. And that, as I mentioned to, I think somebody else earlier this week, Singapore would be a great place to go all electric. You're an island state. I don't think people drive all that far or not very often. You could easily ban most internal combustion engines within the next 10 to 20 years and only sell electric vehicles. So I think no, Singapore has a good chance for doing this. Clearly, this all impacts the grid. You need a better grid if you're going to have large amount of electric vehicles and storage for other devices on it. And we just need to make it happen now, one way or another. So we're going to have to adapt to climate change. We're going to have to adapt to doing things the new ways. And clearly a lot of politicians won't want to do that. But I think we have to move forward. And there's places like Singapore, I think, that can make this happen. Thank you.
Thank you. Also, okay, we got Professor Jan Baliga back. We'll give you an opportunity to continue your discussion later. Now I call upon Professor Ron Hui to share his insight.
Yeah, I think in order to drastically reduce greenhouse gas, we need to proportionally increase wind and solar power or other renewable energy generation. But for the power system to be stable, the emerging smart grid need to balance supply and demand in real time. So in this slide, you can see if we separate the power supply into two groups, the stable power generation are the traditional generators, nuclear power plant, etc. If we want to increase renewable energy sources like wind and solar power, somehow we need to change our control paradigm. Now we have a golden opportunity because globally, many governments have decided to increase the adoption of electric vehicles. And we know electric vehicles have batteries. So what we are considering now is the combined use of solid-state transformer, connecting the grid and a large-scale EV charging infrastructure so that we can utilize all the batteries in the electric vehicle, as well as second life battery that we anticipate to be available in a few years' time when people replace their electric vehicle. And that become a new opportunity for us to use the load, the battery, to absorb the power fluctuation of wind and solar power. In this way, the adoption of electric vehicle and the adoption of renewable energy can grow together simultaneously. So this will become a win-win situation. Now, how can we massively deploy this idea in a city like Singapore? Let me show you this diagram. In Singapore, we have over 1,000 multi-story car parks. And on average, if we talk about 1,000 parking spaces in each multi-story car park, for a 20 kilowatt charger, we have a 20 megawatt load in each building. So we will incorporate a new concept to the solid-state transformer called electric spring concept. The spring will give us the function to absorb and deliver power in order to balance the supply and demand. That means the spring will be the tool for us to tame the intermittency of renewable energy. So if we have 1,000 multi-story car park distributed in the grid in the city, so it will behave like the array of mechanical springs supporting the mattress. That will become a highly robust and stable power grid. And that will allow us to drastically increase wind and solar power. And from our preliminary study, we hope we can increase renewable energy up to 30 to 40%. Now, in a global sense, that can be translated to about 20% of global reduction in greenhouse gas emission. So this will be a proposal that we would explore in Singapore in the next few years. I think that will be my sharing.
Thank you. Thank you, Professor Hui. So now we go to our panel discussion, and just to set the theme of the discussion right, I would like to ask each of the panelists to share your view on how you define the next generation grid, and also what do you think the next generation grid will look like? Would it be a distributed architecture, will you see the blurring of line between the consumer and producer? So I would like each of you to share your view. We start with Professor Baliga, please.
Thank you. So I think I already started off by describing what we proposed at NC State to NSF in the United States. And that's the concept of the microgrid, where it becomes a self-sustaining grid at a smaller scale, which integrates the energy generation through wind or solar, the energy storage, and the users, which are consumers or industries. And to do that, we felt two things are needed that I was describing. One is the solid state transformer to be able to plug and disconnect all these energy storage or energy generation units into and out of the grid. And the other was the fault isolation devices that would isolate any faults in the grid and keep the rest of the grid working. That gives you a lot of resiliency and robustness. So to do all of this, it took 10 years of work, and we realized that it's not just the power electronics that's needed. A lot of communication is needed across the grid to balance everything. So a lot of communication work was done, and a lot of software protocols were also done in order to make this work. So it was a very big effort with 5 universities and 10 years of effort. So what I wanted to convey is this gave a chance for us to establish a methodology to achieve what we're talking about. It's not a completely new idea anymore. There's a lot of work that's been done here, and then we've seen activities like this in Germany and many other places as well. So I think we have a very good place to start if we want to seriously implement these kinds of new types of grids. I can tell you that the biggest challenge I think we are going to face is that the utilities are not ready to accept this kind of a concept. It challenges their traditional architecture, which is to generate power at a large scale and send it over a long distance. And this is not the model that they want to see, where they lose control of the generation, of course, and the revenue that comes from it. So as a consequence, the people who make the devices also don't see a market, because nobody is asking them to sell these devices into the utilities. So this is somewhat of a chicken and egg problem. And I think this is making the current semiconductor industry in the power area very reluctant to get into the utility scale work. Instead, you mentioned the electric car already. So they are very heavily investing in making devices for the electric vehicle, because there's clearly a big, huge market for it. And they are seeing very good reaction to products that they're making. So in some senses, we are working along the lines you mentioned, but in terms of the actual grid itself, that activity is not moving as fast as I'd like to see.
Okay, thank you. Yeah, so I think the challenge will be to get the utility to accept all this new technology. And I also see that silicon carbide transformer would be one of the game changer in this new grid. Yeah, so let's hear from Professor Whittingham.
So I agree with mostly what Jay said. I look at the next generation grid as really a lot of micro grids connected together, so they're interconnected. And the challenges we then face is we need storage for doing the smoothing, but also a lot of the generation comes from large sources. In New York State, we get a lot of our power from hydropower from Quebec. So our plans now building huge wind farms off the coast of Long Island. And all that will then have to be transmitted throughout the state and basically throughout the Northeast. But complicating all that is, as you said, is the utilities. In a state like New York, I think we have 4 or 5 different utilities. It's not clear that they can generate power and necessarily sell that power. So when they put storage in, to them, it's not clear how they can make any money from storage, because it's not considered a generation capacity. But there are third parties coming in already on storage. They're building storage facilities next to substations, and they buy the power at night and sell it back to the grid in the middle of the day when they need it. So it's happening here. Clearly, it's happening in California, the huge facility in Moss Landing. It's basically getting charged with excess solar energy in the middle of the day. Right now, California is generating too much solar, and then they're using it later in the day. So I think we're going to have microgrids, which help us get over some of the things like when we have hurricanes and tornadoes, which can disrupt the major grids. Your little self-contained grid will then still survive those outside activities. So it'll give us more flexibility. It'll hopefully allow things to keep going. But I think the other key thing in the long term is we're going to link all our storage capabilities together, which includes the cars, the trucks, everything. But we've got to get the car makers not to void the warranties if we do that.
Yeah. Okay. Thank you. Yeah. So you sort of extended to say that the future grid is going to be a mesh of microgrid, and so because we have to put all our clean energy on it, and most of them are intermittent, so battery storage as to sort of buffer the intermittency would be something that is important. I have a question from the audience now, directed to Professor Whittingham, and I would like to ask him to ask the question directly. We have this from Olivier Hervier. Do we want to put him on so that he can ask a question on the new batteries? Okay.
It's been an absolute pleasure listening. Hi, panel. It's been an absolute pleasure listening to you all today. I just wanted your opinion on other types of batteries and to what extent you think new batteries that are currently being developed, like dual carbon batteries or other things like that, will be important for the future. And, you know, what, if any, type of battery you think might overtake lithium-ion batteries in the future, given that there are some issues with production and lithium abundance?
Something will take over from lithium ion, but I don't think within the next 10 years. Lithium ion's made in the billions today. Any new technology will have to come in and have a niche market where they can make some money to begin with before they can compete economically. And what's surprising about the grid storage, they're using the expensive layered oxides predominantly on the grid because of weight and space issues, whereas they should be using, in my mind, lithium iron phosphate, which is lower cost, safer, and so on. But I think it's going to be a while before any other technology can knock out. The big advantage of lithium ion, they can put it in trailers, utilities can move it around as they like, and you don't need anybody to look after it. So the facilities I know, somebody sits in an office maybe 100 miles away and just monitors it. And they made a facetious comment where I said, how much work do you have to do to keep this up? Well, we have to go and mow the grass around the facility once a week. And that's it. Basically, don't need any maintenance. And most of these flow systems will need a professional on site to look after them, I think.
Okay, thank you. Thank you, Oliver. Professor Whittingham, I actually have a follow-on question. And recently I read that Form Energy has got funding from the Department of Energy, and they are looking at iron air battery, and they claim that it's going to be 1/10 of the price and 10 times the duration compared to lithium battery. What's your opinion on that?
I would say 90% of what you read on batteries is hype. So be very careful. There's no way they can do it for that cut in cost. One of the major components in the battery is the copper. You've got all your buzz bars, connections, everything else, and the substructure outside the active components is a significant part of the cost. So I think as people eliminate the cobalt and other things, the price will keep coming down. Right now, the auto companies are buying batteries at $100 a kilowatt hour. The goal of DOE is maybe $50 kilowatt hour, the pack level for long storage on the grid. But what the grid folks want, they want it to last 20 years. If it's going to last 20 years, it's not going to be low cost.
Okay, thank you. So I would invite Professor Ron Hui to talk about how you define the grid of the future.
Okay, I think there are a few distinctive features of the emerging grid. First, I think we will see more distributed power generation. In the traditional sense, we have the centralized power generation, but we are migrating to distributed one with more wind and solar power. The second feature will be a change of control paradigm. Traditionally, we have the power supply following the load demand. But with all this distributed power generation, the power company has no way to get all information instantaneously to know how much power generation we have. So we have to change the control paradigm that it will be the low demand to follow the power generation. And this will be the only way we can balance supply and demand and increase the use of renewable energy penetration in our emerging power system.
Thank you. Okay, so we have another question from the audience. This is from Makima. I will invite him to come online to ask the question. Makima, please. Okay.
Hello. My name is Makima. I'm come from Thailand. My question is, in the future, can all the electrical that we use in daily lives come from renewable energy, and how much energy storage that need to support this situation, and why in present the main energy isn't come from the renewable energy? What is the main problem now?
Okay, I'll invite Professor Ron Hui to take that question.
At the moment, we noticed that when the renewable energy penetration reach about 15 to 17%, the power system become unstable because of the intermittency of wind and solar power. So that's why we need a lot of energy storage like battery to buffer this fluctuation. Now, I believe that we still need some traditional power generation because renewable energy is to some extent quite unpredictable. So wind and solar energy is not a reliable source. So we still need some traditional power generation. But with the storage, with clever control of different clusters of microgrid, we may be able to push the penetration of renewable energy up to 30 or 40%. Now, even 30 to 40% globally, it means that we can reduce CO2 emission by around 20% globally. And that is a huge impact in slowing down the climate change.
Thank you. Thank you for the question. I would like to follow on this question for Professor Ron Hui. So from 2001 to 2019, we realized that the solar cost has actually reduced by 89% and wind reduced by 70%. So what do you think will be the dominant renewable energy for the grid?
I think it depends on the location. For Singapore, for example, we have to rely on solar energy because we don't have a lot of wind resources. But in Europe, like the UK and a lot of European countries, they can rely on a huge amount of wind energy. In Scotland, they have huge amount of wind. So I think it depends on the location.
Okay, thank you. And we have another question from the audience.
May I ask something?
Oh, okay.
The answer. Me as a researcher in energy storage, may I ask the user that why you said that we need the energy storage to support the unpredictable about wind or solar cell. So what should that the user need for a researcher to develop in the future?
Yeah, okay, Professor Ron Hui, why
Okay.
don't you take the question?
You need the battery to absorb the difference, instantaneous difference between power generation and the low demand. Okay, so this is the part that we have to absorb. For research in energy storage, there are two aspects. One is the chemical aspect. The other is the control aspect. Okay, so if you are considering doing research in this direction, I think depending on your background, you can either choose the control aspect with the electronic control or the chemistry aspect to develop more powerful batteries.
Right. I will also ask Professor Whittingham to give us some advice on battery research. Please go ahead.
As I tell my students, don't work on what everybody else is working on. Work on something different. It may be risky, but you may make a breakthrough, because there's a huge number of folks working on standard materials. Just try to do something different.
Right. Okay. We have another question from the audience, Chen Ling. Can you put her online to ask the question?
Hi, Professor. This is from Hong Kong, and I would like to ask that for the small generation grids that collected together that you just raised, what do you think that are the most important technical issues that need to be solved?
Okay, I would direct this to Professor Baliga.
So as I said earlier in my presentation, we worked on these technical issues for about 10 years at the Freedom Center and addressed many of these issues. That doesn't mean we solved all the problems. There are still improvements that can be made. But one of the difficulties in the activity was actually making semiconductor devices that can work at utility scale voltages. We're talking about 15,000 volts and even higher. And for most applications like electric cars and home appliances and so on, it's fine to have 1,000 volt capability or maybe a little more than that. So the industry right now is all focused on building those components because there are immediate markets. But for the future, if you want to do something at the utility level, we need to make devices at the much higher voltage level. The other unique thing about utilities is that it's an AC system. The power has voltage that goes in both directions. And that requires semiconductor devices that can work in two quadrants. Most power devices like MOSFETs are built to work only in one quadrant. So there is room for a lot of innovation, some of which we have already done, but much more room to create such new architectures. So if you're interested in working on semiconductor devices, there is still room to make some innovations. And the fact that the utilities are sort of slow in accepting this gives you time to do all this research and produce something that they can use in maybe 10 years.
Okay.
Okay, thank you, Chen Ling, for the question. Yeah, you have another question to ask?
Yeah, yes. And I also want to ask that for the small generation grids, that except for the solar panels to be used as the power source, what do you think other like energy resource that can be has the potential to supply power? Because for me, for example, I'm researching in the energy area, and now I'm researching on like using the water, the droplets or the forge to try to generate electricity. Is there any other possibilities to like supply power for the to store energy in the batteries?
Okay, you're asking whether is solar going to be the dominant renewable, and you have to incorporate energy storage as part of the component. Are you asking that? Is that the question you're asking?
I'm asking the question that are there any other energy resource except for the like solar panels that also has potentials to supply the power in the future?
Right. So alternative renewable. Professor Ron Hui, you want to take that question?
Yeah, at the moment, I think wind and solar power are the two dominant renewable energy resources. Of course, you have hydropower, but again, it depends on the location. I think if you are working from Hong Kong, one of my colleagues in Hong Kong, they are exploring energy harvesting from the salinity between freshwater and seawater. Okay, so this may be another opportunity to harvest energy because there's a energy potential between seawater and freshwater. Okay, so this is one of the new area that my team, when I was in Hong Kong, that was one of the areas that we have been studying.
So for completeness, let me mention some more. One other way people are getting energy is through tidal systems, where water comes inland and leaves, and they get energy from the tidal wave. Another is called wave energy, where just from the waves in the water, they're able to extract the energy. So there are many, many ideas out there that people are making use of and having some success. If you need energy, a lot of energy for a longer time period, then you may want to think about storing water in high hilltops. So you can pump this water up and store it, and then recover that water when you need it and get back energy. So all these very interesting innovations are also being done.
Thank you, Stanley. Yeah, Professor Whittingham, please go ahead.
Yeah, we should not forget that cleanish anyway form that we're not going to get rid of quickly is nuclear energy. It does not generate CO2. And a lot of countries, including France, are dominantly nuclear. And I think New York State's spending billions of dollars to keep their old plants still running. And that's a good baseline load when the sun isn't shining.
Okay, thank you. Yeah, so Professor Baliga, I actually visited NC State some years ago, and I spoke to Subhashi, and I know you have excellent work in silicon carbide solid state transformer. But you said that the utilities are a little bit hesitant, and I believe that they are very concerned about reliability. What's the view on the reliability of silicon carbide MOSFET now?
So if you think the utilities are concerned about reliabilities, you should try to make a product for the motor car companies. They are paranoid about reliability and have always been. So if you want to introduce a silicon carbide based inverter for electric vehicles, reliability becomes the very first article of discussion with them. Of course, performance is taken for granted. If you don't have better performance, they're not going to even invite you to come and talk to them. But then cost also becomes the next item. So the industry has worked very diligently to address the reliability issues, and the companies feel that reliability is now under control for devices working at least up to about 3,000 volts. They are not pushing reliability testing at higher voltages because there's not much of a market for them to spend all that effort. But they feel they've done enough to produce sufficient reliability. And I guess one evidence of this is that Tesla has made an electric vehicle that is using silicon carbide MOSFETs in their drives. And that shows that they have some confidence about the reliability. And I've heard that Toyota is also doing this. So I think the reliability issue for silicon carbide has, the perspective has changed a lot in the last 3 or 4 years.
Okay, thank you. Thank you. I realize that we are running out of time. So before I bring the panel discussion to a close, I would like to ask each one of you, what advice would you give to the young scientists to prepare for the grid of the future? We start with Professor Whittingham.
I think the world is open to them. No, countries will listen, utilities will listen, politicians will listen. You have the opportunity yourself of defining what the grid of the future is. Even if it's just in your local housing environment, put a microgrid in a local village or something like that, and then build that up. But I think if it's smallish, you can probably get it going. But as you get bigger and bigger, you've got to involve the politicians, and it gets much more complicated. But I think as we've had hurricanes and fires, everybody's saying we want microgrids. So if the main utility goes down, we are still up and going. So the students, look at the opportunities out there, whether it's in the storage area or in the electronics. Do something that excites you. Don't do anything for the money, because in the end you won't like it. Do something that really gets you excited, and good luck. Some of us have made it. So it's possible.
Thank you. So do something that is exciting. Professor Baliga?
So I say amen to that. I, in fact, said some of the same comments during my discussion with the small group of scientists. So I think I advise all young people who come to me for some advice. They don't do that very often, but when they do, I advise them to find something they feel passionate about, do the proper homework to make sure that you feel your idea will work, and then try to convince people of the merit of the idea so that they can support you to make that come to fruition, to make it a reality. And I think that'll give you a lot of satisfaction. So I also say, don't do something purely for making money. I think you'll get more satisfaction if it has impact on humanity. Of course, it doesn't hurt if you make money along the way. That's always good.
Right. Yeah, okay. I say amen to that too. Professor Ron Hui?
Yeah, I think for the young audience, you have witnessed the adverse effect of extreme weather now. And I think spending your future in environmental research will be a highly meaningful career for you, and you will have no regret when you look back one day.
Thank you. Thank you for all the interesting discussion from the participant and from the panelists. I think we have a very good insight of what's going the next generation grid is going to be like. It's going to be distributed mesh of microgrid with lots of resilience, reliability, and also I think it will benefit the consumer and the producer in a sense that consumer could also produce energy. Then we call them as prosumer. So it's going to be a win-win situation from the user and also the consumer. So yes, we will look forward to the future grid and then let's have a win-win situation for the consumer and the producer. Thank you very much. It's been an interesting discussion, and thank you all of you for this interesting discussion. Thank you.
Thank you.
Thank you.
Thank you.